Hello, welcome back to my channel. And today I want to talk about like physics and shit. So something came across to me as interesting, intriguing, and it's the idea of redshift. If you're not new to my channel, you'll know that if you watch my videos, that I have other videos talking about the physics of light, the behavior of light, and what light experiences. And so, starting with light, I suppose. We already know that light doesn't experience any time from the point that it's emitted to the point that it is absorbed. What that means practically is that light does not so light doesn't experience time, right? It means that light doesn't experience distance. That means that the dimensions light exists within is not 3D. It is two-dimensional by default. What my hand is shaky. When you remove time, you remove distance. When you remove distance, you remove a dimension of space that you move within. So there is no, uh, depending on how you view it, I guess, length or width. Um, we'll say, I guess, width. We'll view it sideways. Stream of light. So it starts here, it's absorbed over here, but there's no space. The width is gone. It doesn't experience any of this travel. It may experience the length. It may experience depth from from the orientation that we're viewing it from. But there is no length. The distance covered is zero. Zero. So two-dimensional emissions of energy. And I find it odd that despite it being two-dimensional, or rather because it is two-dimensional, it almost speaks as though each field is one-dimensional, a 1D field. So you have, for example, electric field and the magnetic field. They are one-dimensional. And I think this is where zero-point energy comes into play, although I don't know much about that. But putting that aside, you got two one-dimensional fields, one in the electric, one in the magnetic. They oscillate together, making a wave that propagates through space-time in a two-dimensional fashion from one point to another. And then and then it is absorbed by matter, usually. So there's a couple things here. First of all, when a emission of light travels through space-time for a long enough distance, it will redshift. We scientists explain it by the expansion of space-time, saying as a light wave travels through space-time over long distances, as space expands, it is expanding the wavelength of the light emission. So you can have a emission of like regular white light or any other light for that matter, or very complex versions of light, which is typical It's not just visible light usually in space. So you have an emission of light, very high energy, usually, almost always, and as it travels through long distances in space time, space expansion elongates the wavelength of light, causing it to redshift. My question was, where does that energy, when light redshifts down to a lower frequency, a lower energy, go? Where does that energy go to? And intuitively, I wanted to answer into space time that it expands. It is the cause of, or at least a partially a cause of the expansion of space time. It is one answer for what dark energy is. It's literally, I mean, it's kind of right in your face. And this is probably where scientists got the name. I might be like, I mean, I know I'm not exactly treading on new water, but at the same time, I feel like the things I'm talking about right now just are not very publicly known. Um, so, for all I know, that could be where physicists and scientists and astrologists even got that term from. Was dark energy is literally the 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 energy siphoned from a wavelength of light that has redshifted. So the energy in that wavelength goes down as the wave expands. And what I found odd too was that it's interesting in the fact that it seems as though a wavelength literally needs space to travel through, yet, as light were to experience its lifetime journey of traveling through space time, there is no room for a wavelength to propagate. Because when you think about it from the perspective of space, it starts and then it ends. There is no like travel, like, you know, it taking from light's perspective as it travels light speed or close to it, there is no distance for a wave to move through. And yet we in our three-dimensional world experience light. We can see it, we can literally see it, we can observe it, we can document it, we can experiment on it, we can do all kinds of stuff with light, unbeknownst to light itself. It is I wrote this down in a previous video, but it's as though light doesn't know that it waves. All light knows is that it starts and ends, seemingly. And the wavelength is a manifestation of it in the 3D, the depth that we live in. And today I was thinking about redshift from the perspective of matter, because matter experiences redshift, not just energy. And what I found peculiar is how when we experience matter redshifting, space-time condenses, which makes sense. But so if a car goes by, or even a sound wave, and actually it's interesting that a sound wave is three-dimensional, and yet a light wave technically is two-dimensional. But either way, when matter moves fast enough through space-time, space-time will condense to conserve whatever freaking physical authority. I don't know. I don't know how to explain it. I forget the words I need to use. But matter or space-time condenses as matter accelerates more and more. However, when energy, light, moves through space time stretches. I find that interesting. I find that there is, for some reason, this separation almost between light and energy. I mean, energy and matter, mass, energy and mass. It's as though space time exists in three dimensions because light exists more and more and more. It's only getting more because everything, stars are burning, everything is going, you know, fire. And so there's only more light to go around. And that may be partially why space time is continuing to expand faster and faster, because there's still more light, more and more and more. And at the same time, any mass that would try to move very quickly through space-time would experience a condensed version, both internally and any observer external to the mass moving through space-time at high velocity would experience their version of space-time condensing around that object. So it's almost as if any observer is impartial to the effect that space-time were to have. It's only in regards to whether I guess a balance or the dynamic between how much energy mass has as it moves through space-time. And I think ultimately this is what a black hole would break down is, and why things spaghettify, is because as you were to inevitably be traveling at the speed of light, entering a black hole, your mass condenses down to energy. Just pure energy. I think if you were to enter a black hole, you would become pure energy in a one dimensional field of space time. And the interesting thing is, even though the faster you go, the more space time condenses. This is only from a 3D representation of space time, versus if you were to condense the dimensions that we're talking about. So for example, light traveling, or matter, mass, traveling close to or at the speed of light would experience two-dimensional space-time, not three. But that doesn't mean that it doesn't take up less space in regards to the other two dimensions. For example, there are very, very, very large wavelengths of light that exist in space, bigger than the Earth, despite the fact that they only propagate in 2 dimensions. They are very large. So imagine how much larger an entity, a body, whatever you want to call what we're talking about, a thing would be or could be in only one dimension of space time, whatever. If you follow the logic of general and special relativity, I feel as though there is room for quantum, um, for an explanation to how quantum physics works. And I think it starts with energy. I think if scientists sort of honed in on the energy dynamic, instead of trying to make other theories fit into general relativity, dive down into general relativity and use the energy facet to further understand physics, quantum physics, in a two-dimensional fashion, because that's kind of all there is for these particles anyways. I mean, it's almost silly to be thinking about a particle as small as quantum to be three-dimensional anyways. I think I think we're our standards for how impressive quantum information or quantum physics should be are too high. We should lower the standards for what to expect from quantum physics and in terms of how it interacts with matter, mass, and other energy in the three-dimensional world. It's really cool that there's all these scientific technological applications for quantum physics. But at the same time, when people are trying to mesh all these theories together into one big coherent idea, I just don't think that there's anything wrong with this idea, this theory that E equals mc squared, the general relativity and special relativity. I feel as though that they make sense logically, even in terms of quantum physics. It's all kind of held together in a neat little package of behavior for mass and energy, and it makes sense. Anyway, that's my rant for the time being. I hope this made sense. If you agree or disagree, I don't know. Leave a message in the comments. Tell me what you think, and bye for now.